And tonight we are delighted to have as our speaker Edgar Choueiri, Professor of Applied Physics and Aerospace Engineering at Princeton University. At Princeton, he is also the Director of the Engineering Physics Program and Chief Scientist and Director of the Electric Propulsion and Plasma Dynamics Laboratory. He holds a PhD in plasma science from Princeton University. Tonight, he will discuss new launch technologies that have the potential to decrease the launch cost for deep space from about $100,000 per kilogram to just a few $100s per kilogram. He will brief us on the most promising plasma propulsion concepts for taking us cheaply to the moon and then on to Mars, and then the next step, interstellar travel, and then intergalactic travel. Tonight we are indeed pleased to welcome him. Professor.
I want to start by testing. I brought with me a little present for the Philosophical Society. It's a little, not too little, roll of paper. It's actually a map of the universe. It's, as of 3 days ago, it was the most complete map of the universe. It's a single piece of paper that has the mind-boggling number of objects. Pretty much all that we know exists up there. Our little caveat I'll tell you about in a minute. And it measures about a little more than 7 feet long. So if you can please take this hand. Oops. And I want to point out something. And I will explain it. I have a PDF version of this, in case you're wondering. And I will walk you through it. Or maybe I'll fly you through it. Right where your president is standing is literally the end of the edge of the universe. That's about 14 billion light years away from this little dot right here. This little dot right here is the Philosophical Society of Washington Cosmos Center. Now you might think that this was easy to put a dot right here. I had to calculate where that dot is, because that dot actually, this is the surface of the Earth, and I'll explain to you in a minute. This dot moves back and forth like this in 24 hours. So I had to figure out on the day when the map was made, where that dot was. It took me a little while because my graduate students were too busy. So I was able to figure out myself eventually. So I'm going to walk you through this map, but this is a present from me to you. Actually from my university to you, because the people behind this map are wonderful astronomers. Professor Richard Gott from the Department of Astrophysical Sciences, where I'm associated. And also somebody who was a graduate student back then, now he's a postdoc, and Edgar Choueiri. Their names are on the bottom. Okay. And I'm trying to remember this. Testing. And switch out of my presentation into a version of this map, this PDF, and try to give you a feeling what the map is about. I'm going to use this map as a background for my story. My story is about traveling in space. And it's my personal vision, which I think some colleagues would admit that they share it with me. What would happen in 30 years? 30 years from now, what would be, ideally, in my hope, my dreams, space travel, how would it be like? How do we travel in space 30 years from now? So, right here, this is, I admit, it's an Earth-centric map of the universe. However, it uses a technique called conformal mapping to put the entire universe on one piece of paper, using the magic of logarithms. Of course, you're all familiar with the Richter scale. When we say there's an earthquake of 6 on the Richter scale, it's 10 times less intense than one that's 7 on the Richter scale. We all know of that. So on the x-axis, on the y-axis here, there is a. Let me make it a little smaller. Are the units in distance from the center of the Earth. Right here is literally the center of the Earth. This is the solid inner core of the Earth. And that surface that we use, that line right here, is the surface of the Earth. this is 1 Earth radius, and units here on the axis, which is about 6,300 kilometers. The units here are logarithmic, so this is 10 times the Earth radius. And we can keep going on, and I'll come back to this edge. But as we keep going, we're going to go to our planetary system. We're going to go all the way to the edge of the planetary system, move on into our galaxy, to the edge of our galaxy. And as you see, the numbers here increase logarithmically. So every time I go a notch up, I'm going a factor of 10. So pretty soon we have to move from units of Earth radii to units of kiloparsec, which are 1 parsec is about 3 light years, 3.2 light years. So the units will change, and the whole scale, the logarithmic scale, will allow us to squeeze everything we have seen in the sky on a single piece of paper. So, but let's start from our edge of the universe. Start from the cosmos dot right here, which on that day was on this little dot. This map, as I said, is logarithmic. We can keep going into the solar inner core, and if we had 11.5 inches more on this map, we'll be able to put a little dot, starting from a dot, that represents the most central atom in the universe, in the Earth, and that would be an iron atom. And with 11.5 inches, you will have a spectacular map of that atom on the same map of the entire universe. But since my intent is to fly into space, we decided to neglect that part, but it will be spectacular to see. You'll see the entire structure of the atom, of the iron atom, which will be at the center core of the Earth. But let's do a shortcut and start from the surface of the Earth. On the surface, you see right here a bunch of green dots just above the surface, and some more right here on this line. And if you look harder, there are some more right here. These represents every single human-made spacecraft that's not classified, that's flying in space right now. Close to 9,000 dots. Every one of them. And some of them here are notorious. This is the Hubble Space Telescope, many pictures of which have been enchanting us over the years. This is the International Space Station. Remark how tiny the distance is from the surface of the Earth. People think of space, they think of going very far. Actually, driving from here to Boston is further than going up in space. It's about 300 kilometers at the distance. That's pretty much nothing. So those who think of going to the space station as practice for humans to reach something like Mars, which we'll see later on this map, are really very optimistic. It's like Columbus thinking, waking up every morning, going to the Atlantic Ocean, dipping his toes, and claiming he's practicing how to get to America. So for the past 30 years or so, we have been really dipping our toes in space, claiming that we want to explore it. So I'm hoping for a change. I'm going to walk you first to our neighborhood, then come back and tell you what propulsion systems needed to do more ambitious missions than just dipping our toes into the ocean. So let's start by going further. First, these are low Earth spacecraft, orbiting about 300 kilometers up to about 1,000 kilometers. One of them is the Vanguard first, which is the first American satellite. It was launched by the US after the first attempt, which was to catch up with Sputnik, which was a disaster. The first attempt was a disaster. Luckily, the second attempt involved a spacecraft built by Professor Van Allen of Caltech and his graduate students, which, unlike Sputnik, which was a little ball that scared the heebie-jeebies out of people at that time and did nothing, this particular dot would be there for 30,000 years because it's way above the atmosphere, and did the major discovery of radiation belts, which are particles trapped in the magnetic field of the Earth, which we call Van Allen belts. So not only did, even though it was not the first spacecraft in space, it was the second one, it was definitely the first scientific spacecraft that did major discovery in space.
Wasn't Explorer the first? Explorer was the first American.
Explorer, that's right. This is Vanguard 1. Explorer, so that was the second spacecraft after Explorer. Explorer came back and dipped back in the atmosphere. Vanguard 1 stayed. So this is a line of green dots, which represents all the geostationary spacecraft right now in orbit. These are spacecraft orbiting the Earth at the same rate as the Earth. They are 36,000 kilometers altitude. and therefore they stay fixed at one point. They're ideal for communication space, for communication networks, and many of the communication that we use in daily life rely on the spacecraft. Right here, if you look harder, there's another fainter line. These are the GPS satellites, which we use every day in our iPhones and our GPS locators. So this is where humans have been exploring mostly. If we keep going in space, now by notches of 10 every time, we start seeing some human-made spacecraft, less and less. The moon, of course. This is a spacecraft that was instrumental in telling us about how the universe was started. This is a spacecraft that told us about the microwave background, which is the thermal signature of the Big Bang. And we keep going right here, and we get to Mars. I'm going to come back to Mars and talk about it. And then we get to the asteroid belt. Now we're talking about 100,000 Earth radii. Oops, my math has something to say apparently. Oops. And we keep going up through the asteroid belt, and furthermore, we get to the edge of the solar system. Again, now we're talking about a bit more than a million Earth radii. This is on the order of 100 astronomical units. An astronomical unit is the distance between the Sun and the Earth. So this is the size of our planetary system. Here you see Voyager 1 and Voyager 2, the earliest spacecraft launched to explore the deep space environment. Voyager 1 is nearing the heliopause. The chief scientist has argued recently that Voyager 1 was still around. This was launched many decades ago. He claims it's already inside the heliopause, which is the edge of our solar system. Voyager 1 is traveling at a velocity of about 14 kilometers per second. To give you a feeling, this is one of the fastest made human objects right now traveling in space. At this speed, for this spacecraft to reach the nearest star, it would take us 74,000 years. It would take the spacecraft 74,000 years. So this gives you a little of a feel of what it takes to get to a near star. Despite what you hear on Star Trek and science fiction movies, going to a near star, let alone to the nearest galaxy, or outside this galaxy, is an immensely difficult task for propulsion to undertake right now or in the foreseeable future. So we'll come back to that challenge in a few minutes. If we keep now notching up by notches of 10, we get down to something called the Oort cloud, which is very interesting to astronomers. This is a region where a lot of the comets that we know are born. And then we get to the edge of, we get to more stars in the solar system. In our galaxy. So each of these dots represents stars in our galaxy. What you see right here are blue circles. These blue circles represent stars that we know today have planets. Unfortunately, 3 days ago, my bubble was burst, so to speak, by the news that there are 1,200 new planet discoveries by the Kepler satellite, which I'm sorry to tell you is not on this map yet. So maybe in the next edition we'll have a lot of these. Now, you might be wondering, and I'll have to give you a caveat. I claimed initially that this is a complete map of the universe. This is the most complete map of the universe. A complete map of the universe would be very hard to read because it would have so many dots. For example, the asteroid belt would be completely black. Already the asteroid belt has, on this plot, has 14,000 dots, although you cannot resolve them with a printer, all of them. Out of 214,000 known asteroids, 248,000 known asteroids in the asteroid database. The reason why we're able to plot these and not all of them is because this map was done by taking a slice from the equator all the way to the edge of the universe and projecting everything that's within 2 degrees of that slice, plus or minus 2 degrees of that slice. So it's not really a complete map of the universe because most of it will be dark patches. It is an equatorial plane that's going from our center of our Earth, from our center atom all the way to the edge of the universe. Up to here, many of the asteroids are only on that plane, but a lot of the other objects are outside the plane. So for the near-Earth part of the map, it includes all objects except for the asteroids. When we get outside our galaxy, then it's hard to include all objects then we put only objects that are on the equatorial plane. Okay, so let's keep going. Oort cloud over there, and oops. There we go. Now we see the stars that have no planet. Remark here that the closest star is Alpha Centauri. There is no sign of planets there. So if you go there, we'll be quite disappointed, and not meeting the chance of meeting anybody will be pretty much zero. However, closer and closer stars we know now have planets on the order of a few light years away. Right here, this is about 4 light years away, which is about 1 kiloparsec, or 1 parsec. Right here you can see 1 parsec, which is 3 light years away. It's about 4 light years away. The first star ever discovered was right here, PSR 125712, that had a planet. That was more than a decade ago. But now we know a lot of stars have planets. And this line is interesting. This is the line at which that demarcates where our radio communications have traveled in space since the first days of radio. So there are today about 10,000 stars that have received the first emission by Love Lucy, and which is a comforting thought. Right here you can see that many stars with their planets, I'm talking about stars with planets, have received our signals. Again, for them to respond to us, it would take another 85 years of travel back for us to hear the signal. Now, if we keep going, we get to the first here, the Milky Way center. Right here, there's a black hole. This black hole has the mass of about 2.6 million stars. It's the center of our universe. And you might wonder why the distance from here to here is not equal to the distance from here to there. Well, it's because of the logarithmic scale, of course. So we can plot the entire galaxy, our galaxy, on a sheet of paper, and still have enough space to put the rest of the universe. So now we keep going, and now we get to a region where the stars are not any, the dots are not anymore stars, but they are galaxies. So each star, each dot represents millions and millions of stars. And then we can keep going till we get to clusters of galaxies. So these structures, which are on the order of 1 billion light year long, this is the largest known structure in the universe, discovered about 7 years ago, called the Sloan Great Wall. It comes from a Sloan survey of the sky, which each dot right here is a galaxy that's made out of many millions of stars. So you can imagine the scales of involved right here. And all the way to the edge of the universe where we have the microwave radiation. So pretty much going further in space corresponds to going back in time, all the way to the Big Bang. However, I'm not a cosmologist. I'm a propulsion scientist, so I would like to go back to the other end of the universe and then start telling you, with my presentation, what does it take to travel in that space. So here's the map. And the question is, how do we get first from here to here? Because this orbit is a very interesting orbit. Once we get to geostationary orbit, then we can launch spacecraft from there. We can put it, for example, build this, instead of putting a space station right here, we can put a space station right there, which would be much more effective and to explore deeper space. Also, it would be stationary, and there are advantages of being at this altitude. How do we do it today? Today we do it with a very inefficient technology. And one of the first goals of mine in this talk is to give you an idea of how inefficient rockets are. This is a chemical rocket. It's a technology that goes back to the Han Dynasty in China, which are pretty much where fireworks were invented using sulfur and cow dung, which were ignited to produce fireworks. As a matter of fact, these solid boosters are wrapped around the main rocket launcher are nothing but fancy fireworks. They are solid propellant. They are burnt pretty much like fireworks. This structure is basically an entire structure holding fuel. The payload is a small percentage of the entire structure. And I'll give you some numbers in a few minutes. Because the whole thing is, the reason why it's all fuel and structure and only a small percentage of it is payload is because rockets are very efficient and very inefficient, in utilizing fuel to produce thrust. Chemical rocket, that is, and I will explain that in a minute. Right now, I'm going to propose to you a vision for 30 years from now, because we know today that it's very difficult to improve these chemical rockets. People have been thinking about alternative ways to get into space. And one of the most promising, it sounded like science fiction a few years ago, but now it's sounding more and more reality, is a way to get to space that would make, that would make access to space extremely cheap. So imagine an elevator. Pretty much when you go from the ground floor to an upper floor of the building, a cable that's tethered to the surface of the Earth, and it's extended in space 36,000 kilometers, and balanced by the other end by a counterweight of some sort. It could be an asteroid, for example. And if you go through the dynamics, and any physics or engineering student in the audience can work out the dynamics of that structure, as a homework, can figure out that this is a very stable structure because the cable will be taught by the gravitational potential of the planet in such a way where you can slide up and down, exactly like an elevator, payload, extremely efficiently and extremely cheaply, because you can power the structure from power on the Earth or from power obtained from the sun, from the counterweight. Either way, you can pass power to the cable, and using the same kind of technology that we use in our trains or our electrical propulsion on Earth to push a climber up and down, which could contain people or payload. Now, the big question is that how would you make this cable, of course? And that is a material science problem. And a few years ago, it was hopeless to think of something like this. But if you work out the tensile strength, the strength of the material needed to have such a cable, you'll find out it's on the order of about 70 gigapascal. For those of you who are material scientists, that's about 100 times the strength of steel. Today, we know how to build, or material scientists know how to build, what's called carbon nanotube structures that can have even higher strength, on the order of 100 and 110 gigapascal. The little footnote there is that the record, and I just learned at the dinner table tonight from a material scientist sitting next to me, is only 18.5 centimeters. So we have a way to go before we have to 36,000 kilometers. But already, 18.5 centimeters is a huge improvement from the microns a few years ago, where these micro nanotubes were discovered. So they have incredible mechanical properties, which now, this has moved from science fiction to an area where every year there's a conference on space elevators, as they're called, where people discuss the technical issue, real funded engineers and scientists talk about how to build these space elevators. The impact of these is tremendous, would be tremendous, because it would make a ride to space as cheaply as sending a package to the Federal Express, possibly even cheaper, because it's really cargo that's going to space without any expenditure of propellant. This is a picture of nanocarbon tube. This is an atomic structure. It's a very interesting material that has superb mechanical properties and also very good conductor, which can be used for both structural issue and also for conducting electrical power in the spacecraft. This is a plot. I'm going to walk you through it. This is a pretty complicated looking plot. It's made by a colleague of mine called Bob Frisbee, who's known for creating, he's at NASA JPL, he's known for creating complicated plots. But they are very insightful. These plots are known to be extremely dense, but you can spend hours looking at them and get more information. We don't have hours, so I'm going to walk you through this one. We actually created the community, created years ago, informally, the Bob Frisbee Award for the most complicated plot of the year. And Bob has won that award for the past few years. So this is an example. What you see right here is on the x-axis is the launch it takes to cost of launching a kilogram of payload into space. So suppose I want to take this laptop, about 2 or 3 kilograms tops, and launch it into space. It would cost, it's also the logarithmic scale in thousands of kilograms. So right here, to give you an idea, this is the price of gold per troy ounce. This is an old number, and now it's much more than that. So this is an old, gives you an idea, it's an old plot. So this actually is even more. What you see right here are the names of the various rockets the US has, going from the Titan, Delta, all the way to big rockets, the Titan IV and the Space Shuttle. So it costs typically, to put something in low Earth orbit, it costs between $10,000 and $20,000 per kilogram. So if I want to put this laptop in space, it would cost more than transforming having a laptop in pure gold, in 24-karat gold. So that's how expensive it is to put something into space. This is low Earth orbit. This is that little tiny surface of area on top of the surface of the Earth that I've shown you in the map of the universe. That's the dipping our toes in the ocean. So that's not really going very far. Still, it costs about $28,000 per kilogram. If we go, the goal is to make this on the order of a few $100 per kilogram. So the goal is to find technologies, launch technologies, that take us from this horrendously expensive endeavor that only makes few countries belong to the club of spacefarers to an area where any country can have its own space program. And even any company possibly, or even schools can have their own space programs. Of course, there will be an umbrella of some United Nations program, but generally speaking, to make it so cheap that companies can compete in space. This other, again, in the spirit of Robert Frisbee, will complicate it a lot more by showing here launching spacecraft to geosynchronous orbit, or to orbits where you can escape to other planets, which is more interesting for space travel. And there, unfortunately, we're talking about $100,000 to $200,000 per kilogram. So it would cost more than $200,000 to even $400,000 to put just a laptop in geosynchronous orbit if you want to do it. So it's a very expensive endeavor, and there will be transformation in the exploration of space if you can reduce this to something on the order of a few $1,000s per kilogram. And it's, of course, the space elevator promises to do that. And actually, it's the only technology we can now see in the future that can have such a huge reduction in space to space in cost of space access. Okay, so now that I've told you how I foresee, how I dream in my most hopeful dreams, how to access space over the next 20, 30 years in a very cheap way, let's go back to the moon. Now you might wonder why we need to go back to the moon. Of course, one could debate that. I have no doubt, by the way, that China, personally, I have no doubt that somebody goes to China very often, that China would be going back to the moon to stay over the next decade or so. I have nothing to quote physically on that, but I have a strong feeling that they are working on colonizing the moon, so before the end of the decade. So, nonetheless, we have been going to the moon using now since the late 1960s, using the technology of chemical rockets. So now I want to give you a better feeling of why this technology is hopeless. This rocket is the Apollo rockets that usually Saturn V engine in the bottom right here. Most of you are familiar with it, have seen it before. I just want to give you some numbers. This Saturn V weighs 2,800 tons. Only a small percentage of it, 47 tons out of 2,800, contain a useful payload. So there's a tiny little bit of space right here, a capsule containing the equipment and the astronauts. And the rest is nothing but rockets, which are useless except for propulsion. You cannot do science with rockets, you just use them to propel. Only rockets, the fuel, mostly the fuel, and the structure needed to hold the fuel, the tanks. All of it is jettisoned or burned by the time you get to the payload at its intended destination. So this is how inefficient travel in space is using chemical, launching is using chemical rockets. I want to explain to you now why that is so. And for that, I promise that I will only use one equation, and that equation, for those of you who do not like math a lot, I'll be sure to explain that equation in plain English. But first, let me give you a caricature of the rocket effect. And the goal of that caricature in the next two slides is to let you appreciate why rockets are so inefficient, why only a few percent of the entire rocket can be used for payload. This is the most rudimentary illustration of the rocket effect. So imagine a guy, which, let's say, potential astronaut, sitting on a spacecraft-like thing, which is now a platform with wheels. The wheels are intended to just counteract friction, so you can slide easily. You all have the intuition that if this so-called astronaut jumps off the spacecraft will react the other way. Okay? You all know that from standing on rollerblades or experiencing a very slippery carpet or whatever. Now, the problem with this propulsion system is that it's using this astronaut as propellant, and that's not a very good idea. So a better illustration of rocketry is a smarter astronaut who does not use himself as propellant, but rather a stack of bricks. And now you can see him here throwing bricks in one direction, and the spacecraft will accelerate in the other direction. If he keeps throwing bricks, eventually this arrow which represents the velocity will increase. That should not shock any of you from your experience. Even if you're not a scientist, physicist, or engineer, you know from real life that this reaction to this force of things thrown out will give you an increment in velocity. Now, this is the propellant. Now, this is the astronaut, smarter astronaut who's using a rocket effect to propel himself on a spacecraft. And there are two velocities to keep in mind to understand why rockets are inefficient. The first velocity, or speed, is the speed with which the propellant is being thrown out of the spacecraft. It's called the exhaust speed. And I want you to remember that because there's another speed to also not worry about, is the increment of the velocity of the spacecraft due to this rocket effect. So the delta V is the difference between the size of this arrow and that arrow. To repeat, the exhaust velocity is the velocity of the gas coming out of the rocket, in this analogy, which as you can see, we want to make it as high as possible. And the delta V is the increment in the velocity of the spacecraft, which typically we want to increase, we want to be as high as possible to meet a certain space mission. You can show from orbital mechanics, basically how spacecraft travel in space inertially, you can show that this is nothing but a price tag, or each mission in space has with it an associated delta V. For example, to go from the Earth surface to a low Earth orbit, this delta V is 7.5 or so kilometers per second. Okay, so you need to increment your velocity by 7.5 kilometers per second if you were to stay in space by starting from the Earth surface. So to have an idea of that, imagine taking a baseball and pitching it. The baseball will eventually hit the Earth because of the gravity. So imagine now pitching this baseball with such a force that the gravity will curve it, but the curvature of its radius is so large that it actually misses to hit the Earth when the Earth is round. Of course, what will happen, the space will keep going around the Earth and comes back and hits you in the back of the head. And that's called satellite. And that velocity needed to do that pitch is 7.5 kilometers per second. So that's the delta V. Now, this is delta V for launch, but going from low Earth orbit to Mars or to the Moon is another delta V. Each of these missions is a delta V associated with it. So delta V is now a price tag for a mission or requirement of a mission. And exhaust velocity is a technological parameter of a given rocketry or rocket technology. And how to combine, if you know a certain mission, if you have a certain mission in mind, you can calculate the delta V from orbital mechanics, as I said. That's a number you can put on a piece of paper. And if you have a certain rocket technology that can produce an exhaust velocity of a certain kind, you have your exhaust. And these two parameters are all that you need to use an equation called the rocket equation. The rocket equation was developed by a Russian scientist by the name of Tsiolkovsky, who was a math teacher in Russia around the turn of the last century. And he derived an equation which today we give quite commonly to students who are first or second year in engineering or physics. It's called the rocket equation. That's the only equation I'm going to show you. And those of you who do not like math can forget about the math because I'm going to walk you through it with numbers. This is Tsiolkovsky himself. And this is his rocket equation. The first term is the ratio of the propellant mass to the initial mass. This is, you can think of it as the propellant mass fraction. How much of the spacecraft is propellant? Or in terms of your car, imagine if this is 50%, that means 50% of your car is gasoline. So of course you want to make that as small as possible. So because gasoline is only useful for running the engine, you want to put payload in the car. So as small, the idea is to bring that mass fraction as low as possible. The equation tells us that the mass fraction is related by this relationship to the two velocities or the two speeds rather I've shown you on the previous view graph. That being the exhaust. So this is the equation. Now let me give you an illustration. To send humans to the moon, we know from orbital mechanics, starting from low Earth orbit, we need about 12 kilometers per second. The best chemical rocket today can produce no more than 4 kilometers per second exhaust velocity. So the Apollo 11 rockets can give you about 4 kilometers per second, meaning imagine the exhaust coming out from the rocket, traveling at 4 kilometers per second. Princeton town is about 4 kilometers to downtown. So it takes 1 second for the propellant to cross the exhaust propellant to cross the entire town. It's a pretty high speed. However, it's not high enough because when you put that speed, with that speed in this equation, by the way, this is the base of the natural logarithm, E. These are the 22 parameters you need. You can calculate what that ratio is, and you'll find out that for this mission, with this technology, the fuel fraction is 95%, meaning that 95% of your car will be filled with gasoline, and you are squeezed all the way somewhere in a tiny little compartment as a pilot, so to speak. So and this is what's happening exactly in this car. The pilots are squeezed in a small, tiny compartment. The rest is all fuel because of Tsikoff's equation. Now, so this is again the 47 tons as opposed to 2,800 tons. Not exactly 95%, but it's the right order of magnitude because there are some accounting of the structure needed to hold the propellant also, which is not included in that equation. Okay, so let's go back to the moon. So now that I've convinced you that it's ridiculous now to conquer the moon over the next 30 years using the same technology we used 40 years ago, let's talk about the new technologies. And now I'm going to quote from you not things that are so futuristic as nanotubes or carbon nanotubes, but things that we explore in laboratories around the world. Specifically in laboratories, in my laboratory at Princeton. So I'm going to be biased here by telling you about my vision of going to the moon over the next 30 years. The first part, I will use a space elevator. 20 years from now, I hope that technology will be mature enough so we can put the payload, without paying much money, into low, we could use the stationary orbit by just tying it over a cable. Okay. And that is the space elevator part of the trip. Once you get to this altitude, then you can assemble very cheaply a spacecraft. That is, once you are now in the vacuum of space and in microgravity space, you can then rely on much more efficient rockets, which are called plasma rockets. Instead of burning a fuel like a chemical rocket does, you now use electrical forces, electromagnetic forces or static forces, first to create a plasma, and then you use the forces to accelerate the plasma. Plasma is an ionized gas. It's a gas that has charged particles. So you can now take advantage of the fact that charged particles can feel magnetic fields and electric fields, and accelerate them out of the rocket at much, much higher velocities than chemical rockets can. Typically, instead of 4 kilometers per second, you can go to 50, 60 kilometers per second. The reason why you are limited to chemical rockets is because chemical rockets have to burn and heat the gas to a high temperature, and they are limited. You are limited by materials, the melting points of how high temperature you can reach in the combustion chamber of the chemical rocket. Therefore, plasma rockets, which don't use any combustion, just create an ionized gas and accelerate it, can exceed easily more than an order of magnitude higher exhaust speeds. Therefore, the rocket equation tells you that the fuel fraction is much, much smaller. So imagine now your car, if you want to wake up and go to LA, drive to LA, you can imagine how many times you have to stop on the road to fill the gas up, the gas tank up. This is the chemical rocket analogy. If now your car behaves like a plasma rocket, because of the exhaust velocity being so high, the rocket equation tells you you only have to fill your gas tank once. So about 100 times less, 100 times more fuel efficient, theoretically you can be. And you can now go to LA and come back and still have some fuel left with a single gas tank. So, and that part of the trip can be made with plasma propulsion. Now, there are various plasma thrusters out there. When I started doing my PhD studies, plasma propulsion was science fiction. Now, there are more than 139 spacecraft in space that use one form or another of electric propulsion. plasma propulsion is one form of electric propulsion, which is now getting more and more popular. It's been used on many spacecraft, including spacecraft that have met with asteroids and comets over the last years, both from US, Europe, and Japan, including a spectacular mission recently of a Japanese spacecraft that used electric propulsion to land on an asteroid. So, the particular kind of plasma rocket I want to show you is one that is dear to my heart because it started with a graduate student of mine 6 years ago in Princeton, 7 years ago in Princeton. We call that FARA. And it's, that, unlike many other propulsion concepts that I started playing with, many of them end up in garbage bin. Every once in a while, out of 5, 6 of them, some of them merit enough attention to become a PhD thesis. And if they're lucky, they can graduate to more development and research. And this particular engine, the reason I'm bothering you with it is because it graduated from being a PhD thesis to one that's now being researched by a number of companies and NASA. It's called Ferret. And the way it works, first I'll give you just a quick movie of it. And you just see this pulse of light that's going through it. What happens right here, this blue light is a plasma. And the plasma is produced by an antenna. This tube right here is wrapped around a glass tube that you can barely see right here. And when you put radio frequency energy in it, the right frequency, and put that whole thing inside of a bunch of magnets, you can couple energy from the radio frequency to the electrons that exist in any gas. There are always a number of small number of electrons exist anywhere, including in this room, because of radioactivity and cosmic rays. And then you can cause them to oscillate enough to create a plasma. So this part of the engine is a plasma source. They use a radio frequency to create plasma. This plasma, after it's created, comes streaming down into this part of the engine where the rocket effect takes place. And the way it works is very unique because it uses something called the Faraday induction to produce a plasma force, the force of the plasma. These red coils are magnetic coils, and they create a magnetic field that takes the plasma and make it plasma, because it's an ionized gas, feels the magnetic field and can slide along it, very much like particles are attached to magnetic field lines. And it comes in this nozzle-looking structure. At the outside part of the nozzle, you see here a wire that's coiled. That wire is a very specific coil that's hooked to a capacitor that can discharge a lot of energy, creating a very high current very quickly. The current in this coil, outside this piece of glass that's conical shaped, rises by 10 to the 10 amps per second. So it's very high rise time. That kind of rise time is enough to induce in the plasma, using the laws of induction, a current that flows, very high current on the order of many thousands of amps, that flows inside the plasma in the opposite direction as the current in that structure. And because you have now two currents in the opposite directions that repel each other, one current is flowing in the plasma, the other one is in the coil, which is attached to the spacecraft. Therefore, the plasma is repelled away from the spacecraft, creating thrust. It's not a steady state thrust, it's an impulsive thrust. But even your car engine works as an impulsive engine because it creates many explosions very rapidly, and the end result of it is a quasi-steady type of propulsion. The same thing here. You're producing plasmoids very quickly by pulsing the structure. And what you're seeing right here is then first the creation, and then that blue structure is a plasmoid which was formed by induction around a cone, compressed because of the electromagnetic forces, and thrown out. Okay. So this actually works, even though, and this animation I've shown you is very accurate animation of what actually happens in the thruster. What's special about the device? First, this plasma can be made because there's no combustion involved. Can travel at 60 kilometers per second easily. That's 10 times, that's more than 10 times the maximum speed at which the gas, the exhaust velocity of a chemical rocket. So this means that if you snap this on a spacecraft, once you're in low orbit, to go to the moon, you can easily cut down the propellant, required propellant mass by more than a factor of 20 or 30. As a matter of fact, the European Space Agency used a similar engine, not this one, but one called a Hall thruster, to send a spacecraft to the moon 5 years ago. It was not big news because it was just a robotic spacecraft to the moon, but it was big news in my community because it used only 60 kilograms of propellant, enough to put them in in a suitcase. The entire tank was filled in a suitcase. It was a major milestone in the history of propulsion. So the advantage of this engine is, unlike any other plasma engines, aside from having very high exhaust speed, never the plasma touches the electrons. The magnetic field is structured so that the plasma has very high energy, and you don't want it to touch the electrodes because first the electrodes start or the walls start to deflate and erode. The advantage here is that the plasma can be contained away from the walls, and then that makes the whole thing compatible with any gas. So in principle, you can put any gas to this engine. What makes it very exciting for many people, including myself, is that you can use things like water as a propellant. As a matter of fact, in the demonstration, where we put water as a propellant, and the engine worked beautifully. With water dissociates, and the hydrogen and oxygen gases are ionized, and then the same effect happens to create a plasma, and the whole thing works. That means you can go to the moon, and when you get to the moon, you don't have to worry about your propellant. Because now we know the moon caps, the moon has a lot of ice, which you can melt, and then you don't have to carry with your propellant to go to the moon. So this kind of propulsion, using water as for plasma, makes it very practical to use asteroids and use comets sometimes, and the moon and possibly Mars as the source of in-situ propellant because of the existence of water. For me, it was a particular nice turn of events because I started my career at the age of 6 playing with water rockets. And recently my sister sent me a picture of her soda bottle. And this is actually my water rocket, which works this way. There's here a picture of a rocket that you can fill with water, and many of you have seen this. And you pressurize it with water and you let it go. It works on a different effect, but uses propellant. For propellant, it uses water. So it's a full circle for me in my career. So I'm particularly proud of that. Now that I've shown you how to get to geostationary orbit cheaply, hopefully in the next 20 years, and then the next step, how to go to the moon cheaply by combining a space elevator with a plasma rocket using water. Let's up the ante a little bit. This same rockets I've shown you, because they can use water, they can be used conceptually to help us mitigate some of the biggest threats we can face in the long term as a civilization. These threats, of course, are asteroids. An asteroid that's 1 meter size impacts the Earth quite often, a few times a year. One that's about 5 meter size impacts the Earth about once every year. To give you an idea of 5 meter size, when a 5 meter size asteroid hits the Earth's atmosphere, it releases about 15 kilotons of TNT energy. That's equivalent to a Hiroshima bomb. Luckily, that happens in the upper atmosphere, doesn't hurt us very much. But every once in a while, now again, the bigger the asteroid, that's frequent. So imagine now an asteroid that's about 50 meters. 50-meter asteroid actually did come close enough to the Earth's surface in 1908 into Skunga in Siberia. It caused an incredible devastation. Luckily, there was nobody there. It pretty much pulverized an area, a forest area, evaporated trees, the size of modern-day London. Luckily, these events happen once every 1,000 years. It's 50 meters. A 1 kilometer asteroid is enough to cause extinction of life in a major area. Something on the order of 10 kilometers is enough to cause the extinction of the human race. Luckily, these events happen every 65 million years. Last such 10-kilometer asteroid happened 65 million years ago and caused the periods of the dinosaurs, as we all know. However, between the dinosaurs and the period, which is every 65 million years, and the 1 meter asteroid that hit us every few months, there's a whole spectrum of things. And the Congress here, even Congress, it's not known to be scientifically minded, has funded research to track these asteroids over the past few years, and with the goal of getting a catalog of all objects that are near Earth that are larger than a meter diameter, which have an impact. To give you an idea now, the worst scenario, before you really worry about things, seems to be the asteroid that's about 1 kilometer size, which is tremendously scary, which is on schedule to be very close to us in the year 2880. And to be exact, in case you want to plan, it's on March 16th. So, having said this, asteroids are a definite threat, but one that we not need to lose sleep over. One idea about propulsion, now that we have a propulsion system that can use water, which is quite common on asteroids, is to imagine strapping on asteroids a number of these are, by the way, a recent map from 2009 of the number of asteroids being found that are above the stern, about a meter diameter, which are quite nasty if they go further deep in the atmosphere. So imagine trapping, this is a ferret, this is a drawing by NASA showing a ferret design using the antenna I've shown you and the core I've shown you. The plasma comes here, forms, gets squeezed, and gets thrown out. Strapped, a bunch of them, using solar panels on the back of an asteroid, and then using lasers that can ablate the water from the asteroid, you produce a plasma directly from the asteroid, and the rocket then has for propellant the asteroid itself, and produce enough thrust that over a period of a few months will cause a deflection of the asteroid to miss the Earth. Okay. As a matter of fact, the Earth itself, in 7 minutes, moves by its radius in its orbit. So all you need to do is, if the asteroid was to collide with the Earth, you need to deflect its trajectory so it's delayed or accelerated by 7 minutes from impact with the Earth. So it sounds trivial, but in reality, you need to know a lot about this asteroid before and plan a mission well in advance to send these plasma rockets to strap on the asteroid and make it deflected so it misses the Earth. Finally, I want to talk to you about two more ambitious missions. One of them is going to Mars, and the second one is going well beyond Mars to the nearest star. First, going to Mars, again, I would do it the same way. I would use a space elevator to get to the geostationary orbit. And then, to go from here to Mars, which is to give you an idea, is about 40 million kilometers from us, as opposed to the Moon, which is only 630,000 kilometers. So it's quite a different trip. A trip that would take us typically at least about 6 months to get there, going through the radiation of all of that. From a propulsion point of view, it would be much more efficient to do that with another kind of plasma engine. And this plasma engine has been worked on for the past 25 years, and now has reached such maturity that it now is being used quite often in laboratories around the world, and it has been tested in space. It's an engine called the magnetoplasmodynamic thruster, and has the advantage over ferrite to produce very high thrust. What you see here is a rendition of a spacecraft that was designed in collaboration between Princeton, 3 other universities, and NASA. To use the plasma thrusters that we have been developing, called NPD thrusters, which I'll explain in the next graph. What's special about them, these plasma engines use lithium as a propellant, the same material in your batteries, which can be liquefied, vaporized, and ionized. Lithium is advantageous because it's very cheap to ionize. And you can accelerate it using electromagnetic forces in the following way. This is a blow-up of the engine at the end of the spacecraft, which is, by the way, a nuclear-powered spacecraft that has in it a nuclear reactor right here. These are radiators to radiate the waste energy. And right here is a lithium tank, spacecraft that can be filled with cargo or people. And this spacecraft can do the trip to Mars very efficiently and very quickly, on the order of a few months, but do it in such a way that the mass required is a small fraction of, literally on the order of about 20 times less than would be required by a chemical rocket. What's special about this engine is that it uses electromagnetic forces in a very powerful way. We inject lithium from the back, and we strike an electrical arc, meaning current that flows through plasma, which are these red lines that you see right here, between an anode and a cathode. These are the electrodes of the engine. This engine is as big as a little bucket like this. And then if we drive very high currents on the order of tens of thousands of amperes, and this current is so high that it induces its own magnetic field. Because of the symmetry of the device, the magnetic field is in the azimuthal direction, like a ring. And those of you who remember the Physics 101 will remember that when you have a current flowing in a magnetic field, you produce a force using the right-hand rule, as many of you I see are doing right now. So you have the J cross B force, if you follow the right-hand rule, J is going down, B is azimuthal, J plus B will be in this direction, meaning the Lorentz force, for those of you who have remembered physics. It's the same force that acts on an electric motor to turn it. Electric motor will have an armature and magnetic field. The current in the coil is the same thing as the current in the plasma. The magnetic field is the same thing as the induced magnetic field. The product of the two produces the force that turns the motor. Here the force acts as a body force in the plasma. This releases the plasma to very high velocities. And the velocities there are between 60 kilometers per second and 100 kilometers per second. So using lithium with this engine, you can go to Mars very quickly. Here are some very quick picture of lithium MPD thrusters. This stands for magnetoplasma-dynamic thruster, a mouthful of a name for a very powerful device. Lithium, when it's filled with plasma, has a nice property. It emits very strong pink light. And I will show you, this is what it takes to, this is from my laboratory, showing some of my graduate students getting ready for lithium. Is worth it, but lithium is very reactive, so we have to dress in these spacesuits to make sure lithium does not see any air or humidity, because lithium can actually react and explode, produce hydrogen and explode if it's exposed to a lot of air. So we have a very tight safety procedure, but it's really worth it because it's superb propellant for these thrusters. This is a Discovery Channel a few months ago filming a firing of our lithium engine. And this is the light coming out of the engine, shining on one of my graduate students, actually, and the chair of my department, and some of my undergraduate students in my division. And then you can see here a movie of Lenny Cassidy, who is a graduate student of mine who now works for NASA, and showing here the engine ignited, producing plasma stream that's fully ionized, that's being exhausted at 65 kilometers per second, consuming 100,000 watts of power, and turning 60% of 100,000 watts of power into thrust. And that engine is enough to propel a good-sized spacecraft in a very efficiently space, and using anywhere between 20 and 30 times less propellant than a chemical rocket for a typical mission. Okay, so now, if you go back to the I want to finish by giving you an idea of how difficult it is to go further than Mars and further outside our solar planet. Here is a curve that has, remember the propellant mass fraction from the rocket equation, that term on the left that I said is 95% for going to the moon with Saturn V. This is the plot of the propellant mass fraction of a chemical rocket using the rocket equation to calculate this curve versus the delta V. This is the delta V, required delta V for these missions. So to escape from Leo, you need to use about, lower Earth orbit by the way, you need about 60% of fuel. Remember, to go to the moon, you need almost 95% propellant fraction. To go past that is useless, because the entire spacecraft becomes fuel. Okay? So this is why we cannot do this. This is just a calculation done simply with the rocket equation. This is when you do the same calculation with the plasma rocket. And now you can see, oh, now we can not only do Mars exploration, but we can go to Jupiter and make a tour between its moons, something that's impossible to be done with chemical rockets. You can also orbit the planet Pluto, or the devoted planet Pluto, or have an orbiter around Neptune. Most importantly, Titan, which is a satellite that bears a lot of resemblance to the Earth's formation and how the Earth formed. We can send a spacecraft, which is very exciting for many geophysicists and space physicists, how to go to Titan and get a sample and return it to Earth, which can be done for the first time using plasma rockets, because the mass fractions are still manageable. However, you can see right away that, remember, this is delta V. If you want to keep going in space further and further outside the solar system, even that blue line is going to asymptote, and even plasma rockets become useless. Unfortunately, they become useless way too soon, to the point that when we start talking about interstellar travel, even plasma rockets are absolutely useless. So, I want to finish by giving you an idea about travel to a near star. This is a near star, Alpha Centauri, and as I said, as far as we know, there are no planets there. If you get there, we'll be disappointed, but let's see what it takes to get us there. So, this is another version of the logarithmic map I've shown you before, but for our near-Earth environment. This is the sun. Here we are, the third rocket from the sun. Mars, I just told you how we get to Mars using space elevators first, then lithium and PV thrusters. We talked about the moon earlier. Then now, this is another factor of 10, another factor of 10, another factor of 10, another factor of 10. This is here 10,000 astronomical units. And this is here about 1 million astronomical units. This is about Alpha Centauri is about 4 light years away. So it's really a very, very tough trip to make. How can we make it? Well, today, it's hard to think how rockets can ever make it there. Because with even the highest exhaust velocity of a rocket, it would take us something on the order of a few thousand years to make that trip. So there's a conceivable way that, again, relies on material science. The idea is to now send a spacecraft shooting towards the sun. Initially, you can again, send it there using space elevators first, assemble it in low Earth orbit, and then use lithium and PV thrusters, like I've shown you before, to go to the sun. When you get very close to the sun, on the order of few Earth sun radii, you can then deploy what's called a solar sail. Technology is growing very fast, including some tests that have been done very recently in Japan and in the US. The idea is to deploy a very vast sail of the order of kilometer lengths of materials that are extremely special, highly reflective, have very low mass surface density on the order of milligrams per square meter, and then, or rather micrograms per square meter. But they have reflectivity that's such that only 1 photon out of 1 million can be absorbed. So it's an extremely good mirror. Such a structure deployed near the sun will receive such a huge amount of radiation pressure that it will give it a kick to zip through the entire solar system and get to 10,000 astronomical units. Not to the nearest star, but to the nearest area outside, an interesting area past the Oort cloud, or we call that the interstellar precursor mission. But to get there, in these 50 years, with current day technology, we can possibly do it in 50 years. To get there, it's more like 500 years right now. But it's possible, conceptually, that we can use that technology to go to interstellar star if the reflectivity and the mass density are brought by orders of magnitude, at least 1 order of magnitude each. Which means that we can possibly do this trip in 50 years, which is about the lifetime of a human, or half-lifetime of a human, so the engineer or scientist can benefit from the fruit of his or her labor. So still, we're talking about a tremendous trip. Another way of doing it is using something, harnessing the most energetic of all reactions, that of matter and antimatter. And that's combining hydrogen and anti-hydrogen in such a way to cause complete annihilation. You all know E equal mc squared, so mass can be transformed into pure energy, which can, in principle, give you enough energy to get to interstellar distances in the only order of 50 years. We are still very far from here, but some of you have heard that in CERN recently, for the first time, significant quantities of antimatter have been captured and isolated. So this is not pure science fiction, but based on laws of physics that are quite well understood. So now I'm going to summarize what I've talked here about 30 years from now. To go to geosynchronous orbit, which is a distance of 26,000 kilometers, I suggest we start thinking seriously about space elevators. And I hope that will become the way to get to space. It would take a few days, because you're still going at a few hundred kilometers per hour, like train or so, up the scale. And that's the maximum speed, typically, on the order of that number. And that's a rendition of a space elevator, some payload being zipped above the atmosphere on a cable. The next mission I talked about is humans to the moon. And there I suggest we use engines like Farad because they're compatible with water, they're very efficient, they can get you there with a fraction of the propellant, a very small fraction of the propellant. So now we can get to 380,000 kilometers in a couple of days by using exhaust velocity on the order of 12 kilometers per second. This is maximum speed of exhaust. To affect asteroids, we can also use multiple Farads, which can then ingest and digest the ice and water from these asteroids and go to 100 kilometers in 10 months. And with that kind of speed, exhaust speed, you can do those missions, at least we know how to plan them. And with proper protection, this asteroid can be deflected conceptually with these kind of arrays of Faraday that can be mounted on the back of the asteroid. And that's the Faraday engine that the NASA designed based on the concept that we started about 7 years ago. Humans on Mars, 15 million kilometers with lithium magnetotachyl thruster. It's a matter of a few months. If you have enough power, you can do it in a fraction of that time, maybe on the order of a month or so, by doing a power trip all the way to Mars. And then you have to increase, in order to do that mission in that amount of time, you need to increase the exhaust velocity of the rocket by 50 kilometers per second. 250 kilometers per second. And that's the picture of the spacecraft I showed you about. And then I talked about the nearest star. The nearest star, 4.3 light years away, I showed you a mission which has been studied by NASA, by a team of people working on solar sail missions. It can be done 50 years, and it requires increasing the velocity to 25,000 kilometers per second. Both the exhaust velocity and the delta V, which are on the same order. And this is a rendition of that. To get to the nearest, if we go there, we won't be disappointed. But to get to the nearest star where we know that there are planets, they are on the order about 10 light years away from us. We're still refining this number because we're still finding more stars. Now people are analyzing stars to see which of these planets around them are Earth-like. But nonetheless, we need to travel even faster. So to get there in 50 years, we're talking about traveling at 80% of the speed of light. And there's some problems there. To give you an idea, one of the most important problems, even if you travel at 1/10 of the speed of light, 1/10 speed of light, a collision with a pebble, like meteoroids, is equivalent to that pebble becoming the mass of the reactive mass in a fission bomb. So the spacecraft will be completely pulverized if it impacts at a speed of a pebble at a speed of 38,000 kilometers per second. Nonetheless, conceptually, if we can travel there and somehow clear the path in front of us, we can get it. So this gives you an idea of how difficult and how almost impossible it is to get out of our, to get to the nearest stars, let alone getting outside our galaxy. To give you an idea, the characteristic length of galaxy is about 80,000 light years. So even if somehow we can travel at the speed of light, and somehow clear everything in front of us so we're not colliding with anything, it would take us 80,000 years to get out of our galaxy. Irrespective, notwithstanding what Star Trek tells you when you push a button in the spacecraft. So, so we talk about 80,000 light years. So the skeptic scientist in me want to say the word impossible right here. But I've learned over the years, even in my lifetime, things that were science fiction became reality. And my students always remind me that that could be the case. So instead of ending with the word impossible, I'd like to change that and put a question mark. Wow. Thanks for your attention.
So since it's a little hard to hear in this room, when you ask your question, if you would stand, please.
Yes, please.
I really like it, fascinating to talk. I love the idea of a space elevator. I've been seriously thinking about, just for a few minutes, about where you would put the cable.
Ah.
Now, let me go
Yes.
step forward. Okay, I've only been able to come up with two solutions, the North Pole and the South Pole. Now, let me tell you the reason why I began thinking was the GPS satellites, and they are at semi-synchronous altitude,
Yes.
which means that, of course, every time you go through one orbit, you cross the equator of the Earth going up, and you cross it again going down, and then you do it 2 times a day, so you got 4 equator crossings per day. Now, it's not quite exactly half a day, it's actually semi-synchronous, but it's like a half Caesarean day. So it doesn't cross it, it's slowly changing. Well, in addition to those satellites, the GPS satellites, you come to lower altitude, and you can have 12 to 14 crossing that. So the problem of the cable collisions And then the only thing I see, we just have to give up the 90-degree orbits.
Yes, actually the answer is very simple.
One more, I'll sit down. And on the geosynchronous, I suggest maybe a little bit below geosynchronous altitude to avoid the collision problem at geosynchronous orbit, because they've got to cross the equator too.
Yes, well, the answer actually came up with it yourself. All these missions are based on equatorial cable in the equatorial plane, and that's targeted to geosynchronous orbit. So this is for placing spacecraft in geosynchronous orbit. The stability problem has been solved and studied for that mission. So the cable will be on the Earth in the equatorial plane, extending past geosynchronous orbit. Because of geosynchronous orbit, all the spacecraft are synchronized. There's no danger of anybody crossing that altitude.
Is the cable attached from the bottom? I think the
Yeah.
cable is starting down here on the Earth and going up.
That's right, and the cable is co-rotating in the Earth. And so are all the spacecraft in geosynchronous orbit. So the whole thing is turning like a turn here.
Well, the satellites are very, they're going to very slowly change, and of course, low altitude, there might be a cable collision.
Oh, with the new spacecraft. Well, if you look at the density, yeah, with the low Earth spacecraft you're talking
Yeah,
about.
but you said there are 8,000, is actually close to 15,000 objects up there. that-
Yes, but the density, again, space is very big. So the density, and you can calculate the collision, because actually collision rate with large objects is calculated all the time for many missions, because you don't want to lose a mission by bumping into a bolt. And there are quite a few. By the way, space debris is a real problem. I'll need to anyway. So, however, the probability of collision can be quite calculated. So the collision with the cable, because of cross section, is very, very improbable. The collision with the spacecraft, which is much larger, is highly more probable. You can just synchronize the spacecraft or stop it before a collision because you can track these objects. So it's not, space debris is a nuisance, but it's not a showstopper for this kind of technology. Okay, thanks. Yes. The gentleman in the back.
Two basic questions. The ferrite thruster and the lithium MPE thruster require prime electrical power.
Yes. Thank you for bringing this up.
Prime electrical power costs right now about 100 kilograms per kilowatt. Maybe we can push it down to 40 if we're groovy and clever. But what's now the thrust to mass ratio of such a rocket when you have to have 100 kilograms per kilowatt of prime power? Even though you can go from DC to RF at high efficiency, it seems to me you've got a real problem on your hands of getting some serious acceleration. You're not going to do this trip in a few weeks or days because the acceleration is going to be dismal if your thrust to mass ratio is a part per thousand. What's the thrust to mass ratio at the typical design point for a farad or a lithium MPD?
Okay. There have been very detailed mission analysis from my group and also from independent groups in NASA showing how these missions are done, including what's called the alpha, which is the number you quoted, which is the specific mass of solar panels. Now, for solar panels, as you said, it's a pretty high, alpha is pretty high, so you end up ending with very massive spacecraft. So there is for missions to the moon, these engines are quite efficient, and you end up with the mass savings are so large that they overpower the power supply penalty. So the power supply penalty, even with the alphas that reported by 100 kilowatts per kilogram, 100 kilograms per kilowatt rather, these numbers are, the mass savings is so much larger that the mission makes more sense with Farad.
What is the thrust to mass ratio?
That depends, the thrust to mass ratio depends on the mass of the spacecraft. But typically, these engines produce on a few hundred newtons per kilowatt. I'm sorry, a few hundred newtons per megawatts. Right? So yes. However, you don't need that many newtons to move in space.
You're willing to wait.
Yes, you need to wait, that's right. So basically how far you can go is how much power you have. But to answer your question, this is all fine and dandy. You can do these calculations and show that you have to worry about break-even for going to the moon. Past Mars, the solar radiation density is so drops because you're going, it drops as 1 over r squared. So you end up with even the most efficient solar panels will cause the problem that you're talking about, are too massive to be used. Therefore, the only option is nuclear power in space.
Okay, now,
Yes.
nuclear power is prime power. Why not nuclear thermal? There are design points out there in nuclear thermal give you thrust to mass of 6, 7.
Yes, actually, nuclear thermal is a very possible option. I could not cover all the propulsion options out there. As you know very well, nuclear thermal propulsion, for those who don't know, is having a nuclear reaction that heats a gas and then exhausts it. There's a limitation there on the amount of the specific impulse of the exhaust velocity because of the melting problem that you would also have. However, they are very efficient because of a high thrust to mass ratio.
I mean, the specific impulse is in between the plasma rockets.
That's right, in between chemical rockets.
But it has enough m dot that you can actually get some thrust out of it.
That's right, yes. So a thermal rocket fills a very good niche. However, for the 60 kilometer per second mission that we're talking about deep space travel, they are totally useless because there's no exhaust velocity there. So you're right, for the near-term mission, thermal rockets, by the way, thermal rockets were funded for a cycle of going up and down. They're tremendous ideas. They're using, as I said, nuclear reaction to heat gases without going to the electrical cycle and producing enough thrust. But as the gentleman said, they happen to have very high thrust compared to electric rocket, but a lower exhaust velocity, but higher than chemical rockets.
The final question is, if you take your solar sail and you get just a big kick near the sun, you go ripping along at 25 kilometers per second. When you get to the nearest star, how do you plan to stop?
That's right. Yes. Well, actually, you'd be surprised. These maneuvers that we thought of. At lunch, we were talking about them. We're talking about braking and reorienting. Yeah, and there are maneuvers that are planned. And some of the maneuvers do require slowing down by moving the sails, and possibly also for orientation using microthrusters to slow the structures. There's a whole team at JPL, including, ironically, a student of mine, my first PhD student, who left all these plasma-powered engine and working on something as pleasant and as peaceful as solar sail. But these missions are very serious, and even slowing down is taken into account. However, slowing down by a star is not a nearby goal. Our first goal is to get to 10,000 astronomical units. Just get there. Forget about slowing down. Yes. Yes, please. Please. Yes.
Yes. My understanding is that Pluto is 4 days away at 1G.
Pluto is what, 4 days?
At 1G acceleration is 4 days away.
Ah, yes, I guess so.
In terms of the cross-galactic thing, at 1C, time changes, and
That's right. You get there.
anyone on board will experience like
That's
4
right.
days in the trip.
Exactly. Anybody on board who was lucky enough not to collide with a pebble will get there, will be young, and will be younger than his family who left on Earth. That's why there's a resonant compression of time, which is absolutely part of special relativity. That's real, which can come to your advantage if you happen to travel at the speeds. That's absolutely, yes.
You mentioned colliding with a pebble,
Yeah.
but the other problem is that space is full of hydrogen, protons. And
Yes.
as you approach these speeds, that becomes a form of radiation that can penetrate a lot of armor or
Absolutely.
or anything else. So how do you deal with something like
Well, forget about relativity speed radiation. Radiation is even tremendously important for travel to the moon. Travel to the Mars is probably one of the biggest problems. The biggest problem to go to Mars today is not propulsion, and I've shown you one idea of how to get there propulsion-wise. You can even get there with chemical propulsion to Mars, very efficiently, but you can. The biggest problem is radiation. So the space is zipped by bullets of energetic particles, mostly coming from the sun, but also from elsewhere. So even a mission to Mars is prone to be extremely dangerous for human without radiation. Now, radiation can be protected. How to protect against radiation? You can put shields, but shields are massive, and that in space, anything massive is a killer. So one idea is imagine that lithium tank that I've shown you. You need to carry lithium with you for this mission to Mars. Lithium can be very effective as a metal at room temperature. It could be a very effective shield. So imagine the astronauts living in a lithium tank. So the walls of the tank become the propellant. And that's one of the advantages, conceptually, of using lithium as propellant. I'm sorry?
When you consume the lithium?
Yes, when you consume, well, hopefully you will calculate so you consume the lithium in such a way that the dose needed. Actually, to go to Mars, the dose needed on one trip is a few times what's allowable by national standards. It's not going to kill you necessarily, but it would most likely cause some cellular damage. How much and whether the cells can recover is another talk that you should invite somebody. It's a very, very wonderful talk, actually. So a lot of questions are being asked about the ability of cells to recover from this amount of radiation over a period of time. Yes. Please.
You mentioned that there were 137 satellites of missions which already used ion propulsion.
Electrical
You
propulsion,
mentioned
yes.
electrical propulsion. Could you tell us something about it, and how do they get their power? And how did they get the power to use?
They're all solar powered. They all use solar panels. They were launched with chemical rockets. And when I said electrical propulsion, I meant because electrical propulsion is any propulsion that uses electrical power to create thrust.
Is it the same as ions?
Ion propulsion is one type and plasma propulsion, one type of electrical propulsion. But the earlier electric thrusters did not produce plasma. They just heated the gas electrically. And there are two ways of heating a gas electrically. One of them is to put a resistor and flow a gas around it. It's like a space-worthy air dryer. And that's called a resistor jet. And many of the early spacecraft, AT&T pioneered that using these engines developed by a company called Rocket Research, many of which I should add were graduated from my lab. I'm proud to say that a few decades ago.
Velocity on electrical?
On these thrusters, it's a little bit more than chemical rockets. So instead of 3.2 kilometers per second, 3.6 kilometers per second. But remember, this is an exponential relationship. So that's 0.6 kilometers per second can save you a few $1 million a year of station keeping. And then they graduate from resistor jets to arc jets, where you strike an arc, like a welding arc, into a gas and heat the gas. Very low ionization, still not a plasma thruster, but enough to heat the gas. It's an electric thruster. Most of the 139 spacecraft I mentioned, about 90% of them are this type. Over the past 8-9 years, a lot of them are now full-blown plasma thrusters. First time with ion thrusters, I haven't mentioned.
So they have used ion.
Ion thrusters have been used on many geostationary spacecraft, and on the first spacecraft called Deep Space One that went to an asteroid. Right now, as you speak, there's a spacecraft called Dawn that was launched last year using an ion engine by NASA JPL, going to meet two large asteroids.
So right now, this is right now?
Right now, they're flying, and the Japanese use an ion engine to land on an asteroid. And there are other types of thrusters called Hall thrusters, plasma thrusters, that have been used by Japanese, by Russians a lot, and by the Europeans. And the number, it keeps increasing. The further we go into space, as I've shown you from that plot, the blue curve, the more advantageous these engines become.
Two more questions.
Two more questions. Yes, please. Go ahead.
This is somewhat related to the question of how do you slow down when you get there.
Yes.
I learned a long time ago the way you go to any of these places is with a Holman transfer.
Yes.
Are you going to use Holman transfers on some of this part of the link?
Yeah, most of the missions, because you don't have enough power to spark all the time, you'll be using Holman transfer. It's inertial flight. To give you an idea, there's a mission going to Pluto right now. When it gets to Pluto, the entire uses chemical rocks only. There was a decision made a long time ago. It uses chemical launchers to launch it. It's already exhausted most of its propellant because the launch speed eats up all the propellant. So right now it has no propellant. So it costs more than $100 million, and it's going to go towards Pluto. It takes 9 years to get there. Once it gets there, it's going to zip by in a few hours. So it has a photo op with its destination of less than 24 hours. So more than $150 million or so, I don't remember the cost, is to take pictures of a swing by that can, because the chemical rockets are not efficient enough to have enough propellant left to slow you down by Pluto. So this is why I mentioned Pluto orbiter, because with electric propulsion or plasma propulsion, not only you can get there, but you can slow down, fire the engine to slow down and get captured and spend a lot of time taking pictures of Pluto instead of flying by a few hours.
Was there a
Last
question here
question.
in the back?
The space elevator is nice, and
Yes.
everybody wants a space elevator. However, we don't have one yet.
Yes.
There's been no mention of how this plasma technology would be used without the space elevator, such as to just go straight from the surface of the Earth. Is there a problem there? What
Yes, I'm glad you asked that question. And I'm glad that was the last question too, because that question is a wonderful question. And about a few years ago, I got a letter from somebody in jail who is actually a space buff. And he sent me exactly that same question. And it was one of the questions, and the question is that why can't you use plasma rocket to launch from the space of the Earth if they're so wonderful? And I gave the question to one of my graduate students who was walking into, day before he walked into an oral PhD qualifying exam just to test him. And he did figure out the answer. And the answer is as follows. Sorry?
You need vacuum.
Well, not, not you need a power, okay? In order to upward, to give you an idea, if you take a balloon and fill it with air and let it go, there's a master wave coming out, okay? Enough to make it fly. That master wave, if you want to turn it into a plasma, to give you an idea, it will cost about 1 million watts. 1 million watts of power to create that master wave into that gas, air, into a fully ionized gas. So it's extremely expensive to produce the plasma. However, once you get to low Earth orbit, because of microgravity and vacuum, then the forces are very small. Okay? But if you have enough power, we'll go back to Boris's example, if you have power, you can operate in air, there's no problem. But if you have gigawatts of power, terawatts of power, you can, and it's coming in a compact way, like let's say cold fusion box, then of course you have use plasma process to go there. But it's so extremely expensive to ionize a gas. It costs 1 electron volt, 10 electron volts per atom. That's a lot of energy if you know what electron volt is. This is why also we use lithium. Lithium is the cheapest gas to ionize.
So it's not the vacuum, it's the force, there's a lot more.
It's the force, that's right, and the force required more master weight, and then in order to create a plasma, you have to pay for it electrically. So I asked my student to get on the board to calculate how much it takes for a balloon to fly, and it was on the order of 1 million watts. Okay, so this is how inefficient, how expensive it is to produce a plasma, fully plasma, at these master weights needed for launching something. Once you get there, the force required is much less, and therefore the master weight are much less, and with a kilowatt, or 10 kilowatt, or 50 kilowatt solar panel, we have enough for us to do many interesting missions, including going to the end of the solar system, but unfortunately not very much beyond.
Thank you very much. And now in appreciation for your lecture, we'd like to present you with a framed copy of your lecture announcement, which has been signed by all of the members of the general community. Thank you very much. It's a pleasure to have you tonight.